Thank you. Does everybody sign the attendance? Here you go. We are going to pick up this morning on section 1.5 and finish through 1.8 by the end of the week. Before we start, does anyone have any questions yet about the homework or any of the material we've covered to this point? No? Okay. Does everyone... No, never mind. Wrong class. I was about to ask you a question about the permittivity of free space. Different class. So everybody's good so far. No questions? Any questions? Any questions? Somebody? Anybody? Okay. Well, we're going to pick up on section 1.5. We're going to talk about the standard units, and in particular the units associated with the SI system, or the SI stands for French, pronounced Système International. It's like the international body of, governing sciences. It's the in order for all scientists around the world to be able to communicate effectively with each other, they all need to talk in the same units. Okay? Now, how important is that really? Because I'll tell you, I know there are people who are, they're metric all the way. It's all metric or it's nothing. And honestly, I'm good. As long as collars and cuffs match. English units work fine for me. Metric units work fine for me. All you have to do is convert between them. And we're going to learn how to do that this week. But you really do need to understand that it is truly important that you be conscious of whatever units you're working in all the time. How many of you remember a few years ago when NASA went to land a multi-bajillion-dollar Mars probe mission spacecraft? They went to land it on Mars, and instead of landing at a soft, 10 feet per second or whatever, it landed at about 25,000 miles per hour, which is basically escape velocity. In other words, they very effectively shot Mars, literally. They turned the spacecraft into a bullet, and then they turned it into a cloud of debris drifting over the Martian landscape. The folks at NASA really got upset at that point. They wanted to know what happened. Why did that probe fly into Mars at 25,000 miles an hour? And it turned out that one group of engineers was working all in metric, and this other group of engineers over here were working in American units, feet and inches and miles. No one ever noticed. And well, they did notice when the spacecraft crashed into Mars. That's when they finally noticed, oh wait, something's wrong. So the point is, it's important to keep your units straight. And there is a governing body that keeps up with that, and that keeps tabs on and keeps the definitions, maintains the definitions of the standard units, the standards by which all things are measured. You may recall, last class I said, This is a course of science. It's about what you can measure. And fundamental units are fundamental to making any measurement. Now, the Système International, or SI, they start with boy, whoever was here last sure didn't clean up after themselves. In case you don't get the joke, I'm the one who was here last. The first standard unit of measure we're going to talk about is how to measure length. That's a pretty standard thing to measure. I mean, probably the first thing you measured was with a ruler. How long is this pencil? How tall am I? You know, when you were a kid and, you know, your mama would mark your height on the door frame and measure how tall you were. Length is a fundamental, it's something that it's fundamental to measuring, and then it is in fact one of the fundamental units. Now, I've used the word fundamental repeatedly so far in this lecture. Think about what that word means. What is it distinguished from? You have fundamental, foundational, and then you have derived. You have fundamental units and you have derived units. And we're going to look at some of these and the differences. The fundamental units are the foundation. They're the basic units that are defined. They're arbitrary, but they are defined. And once they're defined, then everyone in the world can use them. There are other units that are derived. Who can... Just off the top of your head, just an intuitive guess. Who can think of a derived unit? Speed is a derived unit. You ever got a ticket for driving too fast, then you know all about speed. You have miles, which is length. And then you have miles divided by hours. Miles per hour. Well, hour is a measure of time. And it's a fundamental unit. You cannot take other units and derive time. Actually, that's not a completely true statement because, as you will find out if you're in this long enough, that there have been cases where the SI took fundamental units and redefined them so as to make what was once a fundamental unit now a derived unit, and what used to be a derived unit a fundamental unit. So it depends on how you choose to do it, how you choose to define it. We're going to look at some of that. My favorite is amps, where they took the fundamental unit of charge, a coulomb, and a fundamental unit of time, the second, and said an amp was a derived unit of so many coulombs per second. But then the SI got their hands on it and said, no. The amp is now a fundamental unit, and the coulomb is defined as the amp seconds, or however they did it, I forget. But at the heart of the issue is that there will be fundamental units, however you decide to measure the world around you. You're going to have to start with some foundational basis that you derive everything else from, and that foundational basis is what we call fundamental. We've looked at two of them, length and time. Who can think of a third fundamental unit? Not actually the unit, but the quantity that it measures. Distance? No, distance is length. Yeah. Mass. Mass is a third one. We have mass. Now, I want to stop here and take a moment to talk about mass because first I'm going to take a sip of this ridiculously cold coffee. When you think of mass, well, how would you think of it in terms of English units? If you talk about how much something weighs, you talk about its mass, right? And so if you're going to convert from metric to English, you would convert mass into what? Pounds. And that's what you're going to find if you ask your favorite internet search engine. You know, well, how do you convert kilograms into English? It would give you some, 1 kilogram. It's probably going to tell you 1 kilogram is equal to 2.2 pounds. Now, can anyone tell me why that is wrong? I will tell you why it's not, why it's right. But it is at once both wrong and right. This is I know I'm messing with your heads a little bit, but I really want you to stop and to focus on this question, this issue, because it's important. A kilogram is a unit of mass. A pound is a unit of weight, force. They're not the same thing. Mass is, actually, physicists aren't really sure exactly what mass is, but we do know that it is a property of matter that we can measure. It is a quantification of something that we call inertia, which is just a word we made up to describe the fact that if something is sitting still, it wants to stay sitting still and it takes force to make it move. If it's moving, we talked about this last time, if it's moving, it wants to continue moving in that straight line without acceleration. And it takes force to slow it down or to stop it or to turn it. Mass, when you get into relativistic mechanics and into some of the higher level, more esoteric fields of physics, you're going to find out that mass is actually, mass and energy are kind of pretty much the same thing. In fact, it's probably the most famous equation in all of science. Everybody say it out loud as I write it. E equals mc squared. Energy is equal to mass times the speed of light squared. Now, I know you think that means, oh, that's how you build a nuclear bomb. It's not. Well, it describes the conversion of energy, the energy released when you convert mass into energy. When you build a nuclear bomb, you do not get 100% efficiency. There's bits of matter that's left over when it's finished, after it explodes. That matter did not get turned into energy. If it had, the explosion would have been a whole lot bigger than it was. If you want to, and don't bother trying to remember this is not part of this course, but if you want an example of 100% efficiency of converting mass into energy, you'd have to look at quantum mechanics and the annihilation process of matter and antimatter. When you have an electron that meets a positron, the two meet and they completely annihilate one another. That is the 100% efficient conversion of mass into energy. That's also well beyond the limits of this course. So let's reel it all back in and get back to the mechanical universe that we're studying here. And let's make a point of noting that mass and weight are two different things. Now, as long as we are restricted to the surface of the earth, this is true. On earth only. That's why a kilogram of cocaine is about 2.2 pounds of cocaine. A metric ton is 1,000 kilograms, which is about 200 pounds more than an English ton. That's the important part. The weight of a 2.2 kilograms depends on where you are in relation to a heavier body, this planet. On Earth, it's 2.2 pounds. You go to the moon, that same kilogram weighs significantly less than 2.2 pounds, as do the astronauts who carried it. You go into outer space, into the interstellar regions of space where gravity has become negligible. It doesn't matter how many kilograms you have, it weighs nothing. But it still takes a certain amount of force to speed it up or to slow it down or to turn it, to accelerate it. Because mass does not depend on the force of on the acceleration to gravity. Force is equal to mass times acceleration. In other words, how much force you have to exert in order to produce an acceleration of a mass is the product of the mass and the desired acceleration. This is getting us into derived units. This is a kilogram in the standard SI units. We measure mass in terms of kilograms, and we measure acceleration in terms of meters per second squared. So the force, or the weight of 2.2 kilograms would be equal to 2.2 kilograms times the acceleration due to gravity on Earth. We'll call that 9.8 meters per second squared. And that will give us a new unit that we define as a Newton. 1 Newton is defined. You see the 3 lines, the triple line equal sign, that means defined. In other words, it's expressing that this is a definition. That Newton is expressed in fundamental units of kilograms, meters per second squared. In English units, a Newton would be called a pound. Who knows what mass in the English units would be measured in? What's the units of mass in English, in the English system? You would still measure velocity in units of length, so we'd call that feet. Time is still going to be measured in seconds, so it'd be feet per second squared, times something called a slug. A pound is actually a slug foot per second squared. Okay? Tuck that away in your hat somewhere. You'll probably never, ever, ever need to measure this. No one, I doubt you're ever going to have anyone ask you how many slugs is that object. But now you know that there is an English equivalent. This also introduces the concept of how we end up with derived units. That Newton. When we talk about the force exerted on an object and how its movement is affected by that force will be measured in units of newtons. But the Newton will also be expressed, or is expressible, as a combination of these fundamental units of mass, distance, and time. So we got, for mass, we have kilograms. We've also can measure mass in terms of grams. Kind of the same thing, I know, but there's a reason I'm pointing this out. We can measure it in terms of slugs. Time, measure it in terms of hours, minutes, years, months, days, but universally, in all fields of science, the fundamental unit of time is the second. And it's abbreviated simply as S. Length, we can measure it in miles, yards, feet, meters, centimeters. In the SI units, standard units, it'll either be measured in meters or in centimeters. Everything will always be measured in seconds. Mass will either be kilograms or grams. And I can almost promise you at no point in this course will you be asked anything about a slug, unless they snuck one past me into one of the problems in the book. Okay, but if it does come up, you know what it means. You now know what it is. Now, you'll notice that in both distance and mass, there's a couple of options. Now that's kind of not conducive to a one universal standard system of measurement. Who can tell me why we have these two options? I don't want to erase any of that yet. Yes, basically that's actually if you boil everything down to the brass tacks, that's what it's all about. It has to do with the different fields of study. Because, science is no longer just science. Now it's, well, what field of science do you study? Well, if you're a physicist, you're going to generally be working with how long is this table? How high is that mountain? You know, how heavy is this planet? So you're going to work in units of meters. You're probably going to work in units of kilograms. And since everybody does, you're going to work in units of seconds. That's called the MKS system. Meters, kilograms, and seconds. But what if you're a chemist? What if you're a chemist or a biologist or a botanist? You start measuring the pollen that comes out of a given flower. How many flowers are you going to have to depollinate in order to get to a kilogram? You know, it's going to take a lot. Well, the point is, chemists, biologists, they generally work with much smaller quantities. So instead of working in meters, kilograms, and seconds, they work in centimeters, grams, and seconds. And so you will see sometimes referred to the CGS system of units. And they can be frustrating when you have to start sifting through some chemical journal for a bit of data that you need to finish whatever you're working on. And then you get halfway through all your calculations and realize, oh, they're not talking about kilograms, they're talking about grams. I'm off by 1,000. Hopefully just 1,000 and not 1,000 cubed. I actually, when I was doing my dissertation in graduate school, I threatened my advisor at one point that I was going to submit an article for publication, and I was going to change it to slugs, seconds, and furlongs per fortnight. It can get frustrating, but this is why I'm trying to impress upon everyone that you need to think about the units you're working in always, at all times. Otherwise, you'll end up smashing a bajillion-dollar spacecraft into a harmless little planet that never did anything to anybody, despite H.G. Wells's vivid imagination. Yeah. If everyone turns to page 10. Actually, go ahead and back up to page 9. Let's look at some of these different measurements. And I want to go over some of these prefixes with you all as well. Table 1.1. A neutron or a proton, typically the diameter is going to be 10 to the minus 15 meters. You're all familiar with the scientific notation, right? That's in meters. What would that be in centimeters? A 100 centimeters in every meter, so it'd be 100 times this, 2 more decimal places to the 17. typical diameter of an entire atom, not just the proton or the nucleus, but the whole thing, is going to get you all the way up to 10 to the minus 10. Just as a mental exercise, we're going from 10 to the minus 15 meters to 10 to the minus 10 meters. As a percentage of the volume of an atom, how big is the proton? How big is the nucleus? If you divide 10 to the minus 15 by 10 to the minus 10, anybody know how to do this kind of division in your head quickly? When you're using scientific notation, and I told y'all that scientific notation makes our calculations a whole lot easier. This is a perfect example. When I wanted to multiply 10 to the minus 15 by 10 to the power of 2, what did I do? 10 to the minus 2, I added them. I'm dividing 10 to the minus 15 by 10 to the minus 10. Now I just, instead of adding them, I subtract them. Subtract the denominator from the numerator, and you end up with 10 to the minus 15 minus 10, or minus 15 plus 10, you end up with 10 to the minus 5. That's the ratio. I started to write units. Why would I not write units there? No, I'm dividing. I'm dividing meters divided by meters, and I'm getting a little bit ahead. We'll cover this more in a couple of classes. But when you divide meters by meters, they cancel out. And you end up with a unitless number, a percentage, a ratio. 10 to the minus 5. What is that as a percentage? Writing it out. That's the ratio of the volume of the diameter of the proton to the diameter of the atom as a whole, which is 0.001%. The diameter, comparing the diameters, we're talking 1 part in what? Tenths, hundreds, thousands, 10,000s, 100,000s. 1 part in 100,000. In other words, the diameter of the proton is 100,000 times as big. The diameter of the atom as a whole is 100,000 times as big as the nucleus. In other words, every atom is 0.99999% empty space. And that should give you a hint as to how important field forces are going to be in a future course. Here's a good one. Let's talk about this. A virus is 10 to the minus 7 meters. How big is that? (10 to the minus 7 meters). What is that? Let's use these prefixes. This is a virus. Okay? Using those prefixes. Let's see, where are the prefixes? They're in one of these tables. Page 10. Yeah, table 1-4. 10 to the minus 6 would be a micro. So this is 10 to the minus 7. This is 0.1 micrometer or micron. Micrometer means never mind. Don't worry about it. What's the next one? Nano, 10 to the minus 9. So this would actually be about 100 nanometers. What's the most feared virus in North America today? Well, there's a lot of them. There's H1N1, bird flu, HIV, right? You've all been in, I take it most of you went to public schools. You had sex ed. They gave you the lectures about using the prophylactics to protect you from, safe sex and all that. Let's talk about that for just a minute. That prophylactic is made out of latex, right? A latex molecule is a chain of hundreds of individual molecules linked together in one long chain. That means the interstitial spacing, the space between the molecules in latex, is on the order of 1,000 nanometers. 10 times as big as the virus that it's trying to stop. Now, you probably have this picture in your mind of the latex as being a network of molecules linked together like a big net with big open squares. That's not how they work. Think of it more like a big plate of spaghetti, where each strand of spaghetti is one latex molecule and they're all just sort of wadded together, not structured. But if you've ever had a sister who used a sponge in the bathtub to bathe with, then you have no doubt you go in that sponge and you find that her long, long hair has woven its way into that sponge, and you can pull it and it will just keep pulling out. And so how it got in there is just mind-boggling, but if you've ever experienced it, if you've ever shared a house with women, you know that, or in your case, probably from experience, you've seen this happen. Same thing happens here. That latex will, in fact, prevent that virus from transmitting, but only for a certain amount of time. That that the longer that virus is exposed to that latex, the more time it has to navigate its way and weave its way in between all those long, stretchy latex molecules before it comes out the other side. How many of you have ever heard of doctors and dentists talking about they have to double glove? Where they put on 2 pairs of latex gloves instead of just one? Why do you think they do that? Most people think it's to protect them, it's for extra protection from sharps like scalpels and needles. But think about it for a moment. That needle is designed to pierce skin as easily as possible. You think that one extra little thin layer of latex is going to slow that needle down appreciably at all? No. But when you double the layer, the thickness of the latex, you exponentially increase the time it takes for a virus on the order of 100 nanometers to snake its way through all that extra latex. And it's the time that you're increasing by an exponential factor. That's the point of double gloving. And again, we're getting off subject, but y'all can look at these different examples of prefixes. Now, I actually honestly expected there was going to be more questions than there have been, so What about so far? Any thoughts, questions, comments? Anyone want to participate in this class? Remind me of my days preaching. You know, it's like everybody wants to sit in the back row. Thoughts? Who has some thoughts? Yep. Well, yeah, hopefully, and it'll stay that way as long as we go, you know, in small steps and get every step. As long as we understand everything as we progress through, hopefully it will continue to be straightforward and easy to understand. But we're going to go ahead and I guess in that case, there are no other questions. I'll see you all on Wednesday. Oh, has everybody been online on Canvas? And has everybody been able to see the course and the homework assignments? There is a new homework assignment today. It should be there for you to see. And it's, as always, every week, the new assignment comes out and is due the following Monday. No, you can just bring it and turn it in here. Now, if you, oh yeah, wait, sit back down. I got one or two things more about little housekeeping items. Homework is worth 7 points a week. And as I discussed last time, it's important to show your work. That's what matters. If your homework is late, if you don't make it to class and your homework is late, obviously it's better to turn it in on time. It's also better late than never. If you turn it in at the next class, that's fine. If you want to swing by my office down here in room 11, and there's a box on my office door. You can just turn them in there if you're late. If you can't make it to class, to turn them in then. So don't just blow off the whole 7 points because it's late. You can still earn points. And as I said last time, you can also, once you've completed all of the assigned problems, you can pick an additional problem for bonus points. One more thing. When it comes time to exams, you can have a standard, 4x5 index card that you can write whatever you want, front and back. So you can have, formulas and conversions and prefixes. You can put whatever reference information you need that you feel like you want to have at your disposal on that card. Okay, we're not here to try and, this class is not about memorizing minutia. It's about understanding how that minutia works and how to use it. So, think about that as we're going through these lectures. When we get to exam time, you're gonna want to have all this stuff on that you're going to use on the card. Don't try to find out what the questions are and put the answers on the card. That won't fly. All right, thank you.